Hello again. So today is day 2 of pre-calculus review. It's the last day of pre-calculus review that we are going to be doing. Today we're going to be talking about basic classes of functions and just kind of going over the last stuff in general that we'll need to know from before calculus. And the next video we'll actually be able to get into calculus. All right, let's jump into it. So first, and very, very, very important, we are talking about slope. So slope is a really, really big idea in calculus. We don't necessarily call it the slope though. So once we get to this, we are actually going to start calling the slope the derivative of a function. So a derivative is really just a slope at a point. And so this is the big idea of calculus. So it's very important that we understand the concept of slope. Not that it's a necessarily hard concept. So if we have 2 points, x1, y1, x2, y2, we don't necessarily need to know that notation. What we need to know is m equals y2 minus y1 over x2 minus x1. Once we get to calculus, we are not going to be using this definition anymore, but it's very important to still have that in the back of your head. So this is the formal definition, like pre-calculus style. Now, what we'll do with slope is we will use it to create a line, and we will be using these specific definitions, these two that we have here. There's no changing it up for calculus. This just is what it is. So we have two different types of equations of lines. We have this one called point slope. So that's y minus y1 equals mx minus x1. And then we have slope intercept form, which most of you are probably a little more familiar with, which is just your typical y equals mx plus b, where b is your y-intercept. In calculus, at least in my class, we will mostly be using this one. Now, there are some professors that maybe want you to write it in y equals mx plus b form. Maybe in Calc 2, if you're dealing with stuff like this, maybe you're going to need to do that. Probably not. At least in my class, again, kind of referring back to the first video, I don't really care if you can do pre-calculus and simplified things as much as I care that you can do calculus. So if you can get to this point and plug it into this, I don't really care if you can get here. If you can do calculus, I assume that you can just get there. So if I ask you to create the equation of a line and you put it into this form, you can just leave it like that. I'm okay with that. So this right here is going to be the equation that we're going to be using. Y minus y1 equals mx minus x1. Again, if you use this one, no points taken off. An answer's an answer as long as it's correct. All right, let's do a quick example. So it says, consider the line passing through -3, 2 and 1, 4. Find the slope of the line, find an equation in point slope form and in slope intercept form. So the cool thing about point slope form is you can go straight from point slope form into slope intercept form. You don't necessarily need to remember slope intercept form like the name. You can think of it as y equals mx plus b. I probably will use point slope form, that formal definition or the formal name, just to refer when I'm like saying, hey, let's find the equation of the line. I'm using point slope form. That's just what I'm going to be using. So when I'm doing this, I typically like to write exactly what it is that I'm looking at so that I don't mess up, because sometimes it's kind of easy just to accidentally put the wrong number in the wrong spot. So what I'll do is I'll say this is x1, this is y1, this is x2, this is y2. And so when I'm looking for m, which I know is y2 minus y1 over x2 minus x1, I don't have to do any thinking. I've already written it out. I just need to plug the numbers in. So I see y2 is 4 minus y1 is 2 over x2, which is 1 minus x1 is -3. So this is where we have to be very careful. It's minus a -3 number. 4 minus 2 is 2 over 1 minus -3. When you subtract a negative, it turns into addition. So 1 plus 3 is 4. You can also write this as 1/2. All right, so we know the slope is 1/2. I'm going to go ahead and use point slope form first. So what that says is you can choose either point, any point. You can find a new point if you want to, though probably don't do that. That leaves room for error. Choose any point that you're given and plug that in as the point in point slope form. So point slope form says y minus y1 equals m, x minus x1. where x1 and y1 come from a point. And so I'll choose whatever point. Maybe I'll choose this one just for funsies. I already know m. We always need to find that first. Let's just plug it in. Oh, that's an equal sign. So we'll do y minus y1, which is 2, equals m, which we said was 1/2, x minus -3. So y minus 2 equals 1/2 x plus 3. Now, if I were to ask you to find the equation of a line, a specific line, I'm not going to say exactly what because we haven't gotten there yet. This is an appropriate answer. You don't have to simplify it further. So this is the equation in point slope form. Okay, so this is point slope form. Now, if you did want to convert this to slope intercept form for whatever reason, it's very simple. We can just go ahead and do algebra, right? So we can say, so y minus 2 equals 1/2 x plus 3/2. And then we could add the 2 over and say y equals 1/2 x plus 3/2 plus 2. But we want to combine these two things, so we'll make common denominator. So to get a common denominator with this 2, I want a 2 as a denominator. So to get a 2 down here, I have to multiply by a 2 up there. And so y equals 1/2 x plus, once we have a common denominator, we can just combine the numerator. So 2 times 2 is 4. 3 plus 4 is 7. So 7/2. So if you were to go ahead and try to simplify this, this is the answer that you would get. Again, in my class, leave it like this because honestly, this just gives you more room for making a mistake. And if you had a question on a test that said find the equation of a line and you made a mistake here, unfortunately, you would have to get points taken off even if this was correct. So just leave it like that and make it easy for yourself. All right, so this is a really, really big formal definition. Don't write down the entire formal definition. So essentially, just understand the gist of these things. So this is the idea of a polynomial. It satisfies this form where you have some coefficients and you have some variables to some exponents. There's not really a whole lot you need to know. What you do need to know is kind of in here. So the value n, this guy right here, n is called the degree. So the degree is the highest exponent of a function. And I'll go ahead and write that down. So, oops, that's a highlighter. Even if you were in my class in person, you'd get this. So degree equals highest exponent, essentially just of a polynomial. The constant an right here is called the leading coefficient. I might refer to that a little bit, but you don't really need to know that a whole lot. And then the rest of this is just kind of some general stuff. So degree 2 is a quadratic function. So this kind of is important to have the idea. Anytime you see like an x squared, something with an x squared, that's quadratic. Get this back to yellow. And then if you have some sort of an x cubed, that is a cubic function. Those are the typical functions that we like to just kind of know the idea of what they look like. And those are the kind of toolkit functions that we use to refer to like end behavior and stuff like that. All right. In terms of power functions, a power function is essentially just a single term of a polynomial function. So it's just of this form. So power function of that form. You don't need to know the definition of a power function. Formally, we are going to use power functions a lot in calculus. They're just terms, though. You don't need to know exactly what it is. So just knowing, being able to look at that, and when I ask you to do calculus, you being able to do calculus, that's all we really need here. So you don't need to write a whole lot of this down. Again, it's just kind of conceptual understanding as opposed to like formal, like I'm not going to test you on definitions of any of these things. Our favorite formula ever. So now we have the quadratic formula. This is important to know. Sometimes you will be asked to find x-intercepts. Sometimes they won't be easy. You can't just do a cute little factoring technique. Sometimes you have to use this method. So it is very important that you have the quadratic formula memorized. And that is this whole thing right here. There is a fun little song. If you Google quadratic formula song, I promise it'll get stuck in your head. That's what they use to teach in like middle school and high school. They play the song and then it gets stuck in everyone's head and then no one forgets the quadratic formula. So make sure you know that. This is only applicable when you have a function of this form. So you have a quadratic function where a, b, and c are in those specific positions and it's equal to 0. If it's equal to like 5 or something like that, you have to move the 5 over to the other side. That becomes part of your c. Once it's equal to 0, you can plug in. We also have these discriminant rules. You don't really need to know any of that. You could read through it if you want. The main idea is, so this b squared minus 4ac cannot be negative, which we just know. We know that about a square root, right? A square root can't be negative. It can be 0. It can be positive. You don't need to know if there's 1 or 2 real answers based on that because you'll be able to solve it. You can figure that out just by doing the math. All right, so let's go ahead and take a look now at this idea of a rational number. So a rational function, sorry. A rational function is a polynomial over a polynomial. It's this guy right here. F of x equals p of x over q of x, where p of x and q of x are polynomials. Again, the formal definition isn't super important. Just know that we're going to be working with rational functions quite a bit. So what we want to do is we want to find the domain of this function. We won't be doing this exact thing when we do calculus, but we will be doing very similar things. So this is an important topic. So when you're finding a domain of a rational function, what we need is we need the domain of the numerator, we need the domain of the denominator, and we need where both of those domains are the same, where they overlap. So we will find the domain of, I'm going to abbreviate numerator as num. So we'll find the domain of the numerator, the domain of the denominator, which I will abbreviate denom, and where both are, I guess I'll say valid / both exist together. And I'll show you exactly what I mean. I think that a really good example of doing this is with a number line. This is typically how I teach it. So let's do this. All right. So what I'll do is I'll say, here's the numerator domain. Let's solve this. All right. We have the square root of x minus 4. And what we know about square root functions is that we can never have a negative under our square root, which means that x minus 4 has to be greater than or equal to 0 always. Okay, so that means that x is greater than or equal to 4. Perfect. Now let's look at our denominator domain. All right, what we have is we have 2x minus 12, which 2x minus 12 on its own is just a linear function and doesn't have any restrictions. But because it's in the denominator, we have a restriction, which is that we can't have 0. So that tells us that 2x minus 12 cannot be 0, which tells us that 2x, when we move the 12 over, cannot be 12. And when we divide the 2, we get that x cannot be 6. And so what we want to do, what I typically do, is I'll draw 2 number lines, one for the numerator and one for the denominator. And where both of them, if you were to squish them together, would kind of lay on top of each other, like where that happens is where our domain of the rational function exists. So let me demonstrate. So x is greater than or equal to 4. I'll put a little tick mark here for greater than or equal to means that I can do a solid circle and I'll kind of do above it. Or I can even use a different color and make it a little bit easier. Goes this way. All right, for the denominator, it just says that x can't be 6. So let's say maybe 6 is here. So x cannot be 6, which means that we can have everything over here and we can have everything over here. And so when we're looking to find the domain of the entire thing, I'll make a new one. So this is just of f of x. We want to look at when you smush these two functions together, where the overlap happens. And so essentially, if you took, let's go everything left of 4 and you smushed them together, Well, this doesn't have any valid domain. So you can't say that the function has a domain there because the numerator does not. Where we start is at 4. So we can go ahead and say, okay, we start at 4. And then we have to ask ourselves, like, can we go on forever or do we stop? And we see here we stop at 6. We have an open circle here at 6. We can't be a number at 6. We may have it here, but we don't have it here. And then we see when we go on forever and ever to the right, we do have a domain in both our numerator and our denominator. And so we can do this connector and we can go this way. And so this is the domain of our function. So our domain is from 4, including 4, so we put a square bracket, to 6, not including 6, so we put a parenthesis, union, parenthesis again, starting up at 6, comma, and then we go on to infinity. So this is the domain of our function, using both the numerator and the denominator. We also have this idea of a piecewise function. So when we're looking to graph a piecewise function, what we need to do is we need to look at each of the pieces, and we need to graph those pieces only in the domain that they give us. So what we'll do is we'll just plug in values that they give us in the domain into our function. We'll plot those, and then we will just connect them in the general shape of the graph that we would know it. For example, x plus 3 we know is a line. We would connect it as a line. X minus 2 squared is a parabola. We'll try to connect it vaguely like a U. Now, disclaimer, I'm really bad at drawing, so this is not going to be good. It's kind of a joke with any of the students that I've had in the past. I can't draw anything even close to correct. So I'm going to try my absolute best. All right, so let's go ahead and just try to graph this. So this says x plus 3 for x is less than 1. So first of all, let's go ahead and let's get some axes going. Some nice x and y. Arrows, of course. Here's our x, here's our y. And this is x plus 3 for x is less than 1. So sometimes what I like to do is I'll actually write it off to the side and I will go ahead and plug the numbers in. So we'll always start with the value that we're given, even if it's not equal to that value. So I'll say f of 1 for, let's say, graph 1 equals 1 plus 3, which is 4. But what I know is it's not actually equal to 1 because we can't actually have a point there. So at x equals 1, which I'll say is here, our y value, 1, 2, 3, 4, has an open circle. So if there were to be a point, that's where it would be. But we don't have a point, so that's how we indicate it. Now as x is less than 1, so I'll choose 0. 0, oh, it's doing it again. Let's go f of 0. Plug in 0, that's 0 plus 3, which is just 3. So at 0, we are at 3. And you know what? Let me do a different color for the graph to make it a little bit easier to see. So 3, if we did -1 plus 3, so here's -1 is positive 2. And it really only takes 2 points to make a line. So we have 3 here, and we're going to try our hardest to connect this in a line. Again, apologies, I can't draw for the life of me. That's why I do math. All right. For the next one now, we have x minus 2 squared for x is greater than or equal to 1. So we'll call this maybe equation 2. We will start with the number that they give us, and then we will just continue on in the domain that we have. So we'll start with 1. F at 1 is 1 minus 2 squared, which is -1 squared, which is 1. So at 1, we have a point that is 1. So I'll maybe use blue. And we can have a closed circle here because it says that we can be equal. All right, now we'll do f at 2 is 2 minus 2 squared, which is 0 squared, which is 0. So here's 2, we're at 0. We can do one more. Let's do f of 3. That's 3 minus 1 squared, which, oh, sorry, that's a 2. 3 minus 2 squared, which is 1 squared, which is 1. So at 3, we're at 1. And what we know is that this is a parabola, and so it kind of looks like a U, and so it goes like that. So that's how we would want to graph a piecewise function. We probably won't be graphing a whole lot of piecewise functions, but we will be looking at piecewise functions. We will be looking at specifically kind of the weird parts of the piecewise function. And what I mean is this this part right here. But that's for, I would say, a couple lectures from now. All right, these are the transformations that I mentioned in the last lecture. This is hopefully a refresher from pre-calc. So essentially, we have specific ideas of how things can move. So if you have your function f of x and you either add or subtract, so these two things do vaguely the same. If you add or subtract some constant c, then we're changing our function vertically. So if you're adding c, you're shifting up by c units. If you're subtracting c, you're shifting down by c units. So when I teach this, what I always like to say is anything happening outside of our parentheses, the parentheses being the of x part of f of x, anything happening outside of the parentheses, do exactly what you would expect to happen. So if you see plus something, then you go up. If you see minus, you go down. Anything happening outside of the parentheses is also a vertical transformation. Anything inside is horizontal. And so, for example, if you see these two, which are happening inside of the parentheses, they are horizontal transformations. And horizontal transformations don't work the way you'd expect. So what I say is that they do the opposite of what you would expect. So for example, if you see x plus c within the parentheses, the opposite of plus is minus, and minus usually indicates left. And so you're shifting left by c units. Same here, if you have minus c inside the parentheses, well, the opposite is plus, so you're going right c units. Here you have c times f of x. So this is again happening to your f. This is not inside of the x. So this is a vertical transformation, which means you just multiply all of your y values by c. You don't need to know these specific terms. Frankly, I don't even remember which one is a stretch versus a compression. So just know how to actually do the algebra. If you see c times f of x, multiply all of your y values by c. If you see a c inside, then this is the same idea that I mentioned. It's doing the opposite of what you would expect. So what you're actually going to be doing if you see c times x is you are going to be multiplying your x by something, but instead of multiplying by c, you multiply your x values by 1 over c. And so instead of, I guess, not necessarily multiplication, if you want to think about the opposite of multiplication being division, you're dividing by c. And then these two guys, negative f of x or f of negative x, they go hand in hand. These are reflections. The way that I like to think about these are if you negate one variable, you reflect over the other. And so here, if you negate the y, flip over your x. If you negate the x, flip over y, which is exactly what this is saying here. Those are just some little tricks that I like to kind of keep in my tool belt to make it a little bit easier to actually know what it is that I'm looking at when I'm looking at a function. All right, now we also have these exponent properties. So this is very much so a pre-calculus topic. This is like a high school topic, but I find that a lot of people struggle with this because maybe they didn't have like the best teacher when they learned this. These are very, very important. We are going to be dealing with a lot of like adding, subtracting, like pretty much anything you can do with exponents, we're going to do it. So if you are a little bit shaky about how to use your exponents, anything like that, make sure you do some practice. Reach out. These are such important properties. All right, so let's go ahead and do some examples. So what this says is if you have common bases, which is x, you have x to the m times x to the n, you can actually write this as a single base to the m plus n. So an example is something like if you have x to the 6 times x to the 3, you can write this as x to the 6 plus 3, which is x to the 9. You can also use an actual numerical example. So if you have like 2 cubed times 2 squared, this is the same thing as 2 to the 3 plus 2, which is 2 to the 5. Here, if you see division, it's just kind of the opposite of this one. If you have x to the m over x to the n, and again, this only works if you have the same base. If you have like x and y where they're two different numbers, it doesn't work. x to the m over x to the m, you want to combine it into one base, you subtract the exponents. So this turns into x to the m minus n. And so an example is we'll use a y maybe to the 10 over y to the 4 equals y to the 10 minus 4. It's y to the 6th. Or we can have a 5 to the 3 over 5 equals, well, something that we have to remember is that if there is no exponent attached to a number, there's an implied 1. So this is 5 to the 3 minus 1, which is 5 squared. If you have a base and an exponent, and that is to an exponent, so we call this a power to a power, then you multiply the powers. A lot of people try to multiply these. That's incorrect. So let's multiply when we have two exponents next to each other. And so that could be like x to the 3 to the 8, which is like x to the 24. This one is going to come up quite a bit. So anything at all to the 0 is going to be 1. So if you have y to the 0, it's 1. If you have 6 to the 0, it's 1. Anything to the 0 at all will be 1. This is also going to be a very, very important property. We're going to be needing to use this a lot. We're going to need to know just when to use it. So this says that if you have a negative exponent, you can rewrite it as 1 over, and then you can change the exponent to make it positive. So you would essentially negate the exponent and can change what part of the fraction you lie in. Now, we might not necessarily be going this way, but if you have something like this, we will be going this way. And what I mean is you can have something like 1 over x to the 7, but we don't want it like that. A lot of times in calculus, we try not to work with fractions if we don't have to. We would like to keep it as a single term. And so what we'll do is we'll rewrite this as a negative exponent. So to do that, you take the exponent and you negate it, and you can change the part of the fraction you're in. So this can turn into x to the negative 7. All right, that's the big, big idea of what we want to be doing here. Then these last two are very similar. So if you have two different terms, x and y, and that's raised to a power, it is essentially like distributing your exponent. So you can just distribute that power to both of them. So if you have like m times n to the 3, that's the same thing as m to the 3 n to the 3. Or if you have even 6x squared, as so, where it's quantity squared, it's 6 squared, which is 36 times x squared. And same idea here. Again, it's just kind of distributing. So you can have x over y to the 12, which is just x to the 12 over y to the 12. Or you can have something like 5 over 3 squared, which is 5 squared, which is 25, over 3 squared, which is 9. Yeah, be sure to have common bases when you are combining your exponents, and definitely be conscious of the fact that we can use variables or numbers. That's why I tried to kind of use both as an example. So these are very, very important rules. All right, now the last kind of big topic that we want to cover today is going to be factoring, but factoring encompasses a lot. So we have 3 different methods that we want to use in order to factor. So we have this method called the greatest common factor. We have the x squared plus bx plus c method, and then we have the quadratic formula, which we've already kind of touched on. So we have this idea of the greatest common factor. So the definition of the greatest common factor is the largest polynomial that divides evenly into the polynomial, essentially, that you're given. Okay, and this is the how-to. Given a polynomial, factor out the greatest common factor. So the idea is we want to essentially identify which one out of these 3 methods we want to use. And the greatest common factor is kind of the easiest one to know, because with either one of the x squared or the quadratic formula, you're going to see some sort of a quadratic expression or quadratic-like expression. With the greatest common factor, you could see some crazy expression with x's, y's, z's, and it looks nothing like those two. So you would know right off the bat that you're going to want to factor using a different method than your typical. So for this, you'll identify the greatest common factor of the coefficients first. So look at the numbers, see what the largest number you can pull out of all of them is without taking too much out. You'll look at the variables and do the same thing. What is the largest that you can take out of everything? And then you're going to kind of put them together. So combine the coefficient and the variable. And then once you go ahead and find that, this does say to determine what the GCF needs to be multiplied by, but essentially what it means is another way of saying 4 is to divide the GCF out of given polynomial. That's a lot easier. So you take every single term that you have and you just divide by the greatest common factor that you have, and what's left should be the simplest factor. And if it's not, you factor again until you have the most common or the simplest factored expression. All right, and then 5, write the factored expression as the product. So essentially that just comes right from factoring it out. So write it as a product of the greatest common factor and whatever you have left. I know that's a lot of words, makes no sense probably unless you're very familiar with it. So let's do an example. Oh, well, I guess let's first tell you how to do the other ones and then we'll do an example. Sorry. Now, if you're given something of the form x squared plus bx plus c, so we know you can have quadratic expressions of the form ax squared plus bx plus c, but the problem is if you have this a that isn't 1, so here a is 1, a equals 1 here. If you don't have a as 1, factoring becomes a lot harder if you're trying to do it like this. So I'm going to omit the discussion about how to factor using like the grouping method. It's just a lot. That's why we're going to do it using the quadratic formula. So here, in order to factor, what you want to do is you want to list factors of c. So find some number c, and you're going to have c, and you're going to have like c times 1, 1 times c. And you're going to find all of the factor pairs, essentially. Oop, I want to erase that. You're going to find all of the factor pairs that multiply to whatever value it is that you have. All right. Once you have all of your factor pairs listed out, you're going to find a pair that adds to your b value, and that's including the sign. So if your sign is negative here, you need a pair that will add to the negative value. All right. So once you find that pair, you can go ahead and circle it, and you can write it as x, whatever the sign is here, and then x, whatever the sign is here. And note, not all polynomials have a real factored form. And an example of a polynomial that wouldn't have a real factored form is a quadratic expression that looks like this, or a quadratic equation. The factors come from the roots or the x-intercepts of the polynomial, and this one clearly doesn't. So this would have imaginary roots. If you were to use the quadratic formula, you'd get a negative under your square root. So we're not really going to deal with that. And then lastly, like we've already kind of touched on the quadratic formula. Again, negative b plus or minus the square root of b squared minus 4ac all over 2a. A can't be 0. But if a was 0, then we would have a linear equation. So this wouldn't be quadratic anyway. So we need to put that in, but we don't really care about that a whole lot. So if you're looking to factor and you have this form right here, again, if you know the specific way of factoring using ax squared plus bx plus c, and you don't want to use a quadratic formula, go for it. If you're a little bit rusty, this is the way that I recommend doing. So what you would do is you just want to go ahead and plug everything right into here. So yeah, like this says, make note of what a, b, and c are, substitute into the equation, and then solve it. You'll get that x equals, so like say you get like x equals 3 and x equals negative 2. And if you are asked specifically for like a factored form, you can go ahead and kind of reverse engineer the factored form. If you want just the x values, those are them. If you're looking for a factored form, you can go ahead and say, okay, x minus 3 equals 0, x plus 2 equals 0. And so therefore it would be x minus 3 times x plus 2 equals 0. So you just kind of reverse engineered it. Typically you want these numbers though, so it doesn't really matter quite so much to like reverse engineer it. All right, so this is the last thing we'll do for today is going to be factoring some expressions. So the first one is this GCF. This is the one that I think is probably going to be a little bit trickier to understand. So when I say factor out the greatest thing that you can, I'm actually asking for like the greatest minimum, if you will. So what that means is if you see 6, 12, and 18, we'll look at the coefficient first. we want the greatest number that can be pulled out of everything. So you might be inclined to say 18, but then if you try taking 18 out of 6, if you try dividing 18 out of 6, you can't do that. 18 doesn't divide out of 6 evenly. But if you look, 6 does divide into 12, right? 12 divided by 6 is 2, and 6 divides into 18. 18 divided by 6 is 3. And so the greatest coefficient that can be pulled out of everything is 6. And so I'll say equals. And so this is where we're going to start to write the greatest common factor. So I'm going to say 6. That's the first part of our greatest common factor. Next, let's look at the x's. We want the greatest thing that can be pulled out of everything, which is going to be the smallest number that everything has. So here we have an x. We don't see an exponent, which means it's to the 1. We see an x to the 2, and we see an x to the 3. Obviously, we can't take 3x's out of 1x. We can't take 2x's out of 1x. We can take 1x out of 1x. We can take 1x out of 2x's, and we can take 1x out of 3x's. Therefore, our greatest common factor is just x. You can't take anything else out because the greatest number you have in this term is just 1. All right, lastly, we have this term with a y. We have y squared here, and y cubed here. Well, we could take a y squared out of this. We could take a y squared out of that. And we can take y squared out of that last one. We can't take y cubed out of the first two. And so the greatest common factor of the y's is y squared. And to find what's left, we want to divide this term, which we just determined is our greatest common factor. I'll even write that. G, C, F. This is our greatest common factor. We will divide each one of these three terms by our greatest common factor to figure out what's left. So 6xy squared divided by 6xy squared is something divided by itself, which is just 1. That's like 5 divided by 5. It's 1. All right, 12x squared y squared. Well, 12 divided by 6, and we'll keep the sign. 12 divided by 6 is 2. X squared divided by x is using that rule of subtracting exponents. So that's 2 minus 1. That's x to the 1. Y squared divided by y squared is the same thing divided by itself. That's just 1. So I'm not going to write it. Then we'll keep the minus. 18 divided by 6 is 3. X cubed divided by x is subtraction of the exponent. So 3 minus 1 is x to the 2. And then we have a y cubed minus y squared is subtraction again. 3 minus 2 is just 1. Therefore, this is our factored form. And we can check to make sure there's nothing else we can pull, right? So 1, you can't take anything out of that. There's no x's, there's no y's. Therefore, you can't factor this expression whatsoever. So this is the simplest we have. All right, for this one, we're going to want to find two numbers that multiply to -5. So what I do is I write -5 and I find all of the factor pairs that I can. Because it's negative, that could be -1 and +5, or that could be 1 and -5. And because 5 is prime, there's nothing else we can do with that. So we need to find out of these two what adds to -4. -1 plus 5 is +4. That doesn't help us. 1 minus 5 is -4. That's our pair. And so that tells us that this is, well, we can go ahead and put in our two parentheses, x, x, and we can just go ahead and plop in our two values. So +1 minus 5. Okay, this last one here, again, if you know how to factor it using other methods, you can go ahead and try. I'm going to use a quadratic formula because I see a number other than 1 before our x squared. So we have x equals -b plus or minus the square root of b squared minus 4ac all over 2a, which is -15 plus or minus the square root of 15 squared minus 4 times 4 times 9 all over 2 times 4, which is -15 plus or minus the square root of 15 squared is 225 minus, let's see here, 4 times 9, let's go, is 36 times 4 is, I don't know, let's use a calculator. I could very easily do that, but I don't know. I don't want to. My phone's not working now. Sorry, guys. So we have 4 times 4 times 9, which is 144. On a test, obviously, the numbers would be easier. Over 8. Also important note, obviously 8 and 15 aren't divisible, but if it were divisible, you would not just be able to divide these because you have another term here. So just be mindful, don't divide this 8 until the very, very end. All right, so then 225 minus 144 is, this gives us negative 15 plus or minus the square root of 81 over 8, which is negative 15 plus or minus 9 over 8. This is where you can now go ahead and separate it and say, okay, so x equals negative 15 plus 9 over 8, and x equals negative 15 minus 9 over 8. So negative 15 plus 9 gives us negative, let's see, 8 over 8, which is 1. Negative 15 minus 9 gives us negative, what is this, 24 over 8, I believe, which is negative 3. So these are our x values. All right. Again, if you have any questions, feel free to reach out, and I'll see you in the next video.